Okay. So, students, last week we are discussing about that divide conquer method for efficiently calculate the discrete Fourier transform. So, the whole purpose of the divide conquer methods is that can I improve the efficiency of calculation of discrete Fourier transform. As you know that if I direct compute DFT, the computational complexity is the order of n square, means number of multiplication is nothing but a n square and number of addition is n into n minus 1. So, n square complex multiplication, again if I convert it to the real multiplication, it will be 4 into n square. So, I want an efficient algorithm which the computational complexity will be reduced compared to n square. So, divide conquer method is one of the methods that we have seen that this method can improve the efficiency of calculating discrete Fourier transform. So, those I can say the fast Fourier transform. Now, today we discuss about an Peschel algorithm which is commonly known as an FFT algorithm, which is called Radix-2 FFT algorithm. So, today's lecture will be on Radix-2 FFT algorithm. So, if you see this term contain two words, first word is called Radix-2, next one is the FFT algorithm. So, two phrases I can say. So, Radix-2, what do you mean by Radix-2? What is the meaning of an Radix-2? Now, suppose I say that what is the meaning. So, I am explaining what is the meaning of Radix-2. Now, if I say the length of the DFT is n and n can be expressible in term of 2 to the power v, where v is an integer. So, in divide conquer method, I said the limitation is n should not be a prime number. Here I said the limitation in Radix-2, I said n can be expressed in 2 to the power v. So, if I apply the divide conquer method that n is equal to m into L, let us say m is equal to 2, then L is equal to n by 2. Or if I say L is equal to 2, then m is equal to n by 2. So, whatever I can say. So that if I say that m is equal to 2, then the entire length of the signal is divided into two sections, or L is equal to 2, m is equal to n by 2. So, what I said that if my n is expressible in 2 to the power v, v is an integer, then I can compute discrete Fourier transform of n point by dividing whole n in every time by 2. Since I am dividing the sequence in every time 2, that is why it is called Radix-2 algorithm, or I am expressing n as a 2 to the power v term, that is why it is called Radix-2 algorithm. Okay. So, every time my whole length of the signal will be divided by 2. Now, as you know, think about who have already done the binary search algorithm. What is binary search algorithm? That in normal search, if the computational complexity is n, then in binary search it is nothing but a log 2n, because every time I am dividing the sequence in two parts, then I apply the search algorithm. So, that reduces the computational complexity. Here also every time I divided the sequence in a two sequence, and that reduces the computational complexity. So, in Radix-2 algorithm, what we said, the let n is represented in 2 to the power v, where v is an integer, m equal to 2, then L equal to n by 2, or m equal to 2, then L equal to n by 2. So, whatever you can say divide conquer methods, either m or L, m is the number of column, L is the number of rows. So, this procedure that divide the signal in two terms, let us n, then n by 2, n by 2, then n by 2 can be divided again. So, n by 4, n by 4. So, this procedure will repeat unless I get one point sequence. So, 2 to the power v, I am dividing the sequence in a two way every time in 2. Let us say I said I have a sequence of length 8, length n is equal to 8. So, how do I express n? N is equal to 2 to the power 3. So, I have a sequence length 8. So, first time I divided it is 4, 4. Second time I divided it is 2, 2. Third time divided it is 1, 1. So, if you see how many division is possible? 3 times. So, that is called number of stages. So, what we are dividing? We are dividing the either input sequence or the output sequence. Let us talk about the input sequence. So, what we are doing? We are disseminated the input signal. So, when we divide the input signal, then we call dissemination in time, disseminating in time. Or if I divide in output signal, then it is called disseminating in frequency. So, let us say I describe the disseminating in time algorithm first. So, what is required? We split the n point data sequence into two n by 2 point data sequence f1n, f2n corresponding to the even number and odd number. So, what I am doing? I am splitting x of n in two data sequence dividing by 2. Since the sequence is expressed in term of 2 to the power something, that is why it is every time is divisible by 2. And when I divide, when I disseminated the signal, time domain signal, then it is called disseminating in time algorithm. So, what is the algorithm? So, how do I do that? Let us say go into it. So, what is there? I have x of k is equal to, you know, n equal to 0 to n minus 1 x of n w n n k. So, this is discrete Fourier transform, n point discrete Fourier transform. This is n point discrete Fourier transform, where omega n is equal to e to the power minus j 2 pi by n. Okay or not? So, what I said, I want to divide the sequence in a two sequence. So, x n has a length of n. So, x n varies from 0 to n minus 1. So, x n has a length of n, capital N, and n in the form of 2 to the power something, 2 to the power v, v is an integer. So, n is divisible by 2. So, let us say I want to divide this x n into two parts. So, how can I divide? Let us say, so n is an index. So, how can I divide it? So, you cannot say that okay 0 to n by 2 and n by 2 to, so it is sequential division. So, let us say instead of doing that, I am accessing the signal, or I am dividing x n in term of two sequence. One is called even sequence, another is called odd sequence. So, I can say x of k is equal to n equal to 0 to n by 2, even sequence also divided by 2, length is n by 2 minus 1 x of n w n n k even. This I am accessing the signal which are even. Now, I am accessing the signal n equal to 0 to n by 2 minus 1 x of n w n n k. I am accessing the signal which are odd. So, what is odd? Index of the signal is odd. So, here x of n, here x of n where n is even, here x of n where n is odd. So, index of the signal, so x n is stored in a memory location I am accessing the signal even index, odd index, even index, odd index. So, if I say that in mathematics, how do I write an even number? So, I can say that n is equal to 2m represent the even number where m is also an integer, and n is equal to 2m plus 1 always represent an odd number which is where m is also an integer. So, I can say if m is varies from 0 to n by 2, I get n by 2 number of even number, and m is varies from 0 to n by 2, then I can say n by 2 minus 1, I can get n by 2 number of odd number. So, I can say x of k can be written as, so x of k can be written as m is equal to 0 to n by 2 minus 1. So, x of n, I am accessing the signal which are even. So, x of n is replaced by 2m, x of 2m into omega n 2mk plus m is equal to 0 to n by 2 minus 1 x of 2m plus 1 into w n 2m plus 1 k. So, n is replaced by 2m and n is replaced by 2m plus 1. So, for odd it is 2m plus 1, for even it is 2m. Now, if I do that, so how do I can write down this one? M is equal to 0 to capital N by 2 minus 1 x of 2m into w n by 2 mk. Can I write that or not? So, what is there? Now, I know what is w n. W n 2 mk is nothing but equal to e to the power minus j 2 pi mk into 2. So, 2 is again there divided by n. So, I can easily write down e to the power minus j 2 pi mk divided by n by 2. So, that is why I write n by 2 here plus m equal to 0 to n by 2 minus 1 x of 2m plus 1. So, there is w n 2 m k. So, w n 2 m k into w n k. Again this can be written as this one. So, I can say if you see this one is an DFT equation whose length is n by 2. So, let us say this is f1k and this one is also an DFT length whose length is n by 2. Let us say this is f2k. So, how can I write? I can write x of k is equal to f1k plus wnk f2k. Now, say x of k varies from 0 to n minus 1, but f1k the length is n by 2 and f2k length is n by 2. So, if the length of the DFT is n by 2, then n by 2 is the period. So, I can say the f1 k plus n by 2 is equal to nothing but f1 k. Similarly, f2 k plus n by 2 is nothing but f2 k. So, I can say that x of k is equal to f1 k plus f2 k into omega n k for k equal to 0 to n by 2. Now, for x of k plus n by 2. So, k varies from n by 2 to n minus 1, because x of k is varies from 0 to n minus 1 minus 1. So, it will be n minus 1. So, I equal to f1 k, you know the k f1 k plus n by 2 is nothing but f1 k. So, it becomes f1 k, f2 k, because f2 k plus n by 2 is nothing but f2 k. So, I will not compute f2 k again, and Wn to the power k plus n by 2. Now, what is Wn k plus n by 2 is nothing but a Wn k into Wn n by 2. So, what is this one? Wn is n by 2 is equal to e to the power minus j 2 pi by n into n by 2. So, n cancel, 2 cancel, e to the power minus j pi, which is nothing but a cos pi minus j sin pi. So, cos pi is minus 1. So, I can say this can be written as f1 k plus f2 k into Wn k minus 1, because Wn n by 2 is equal to minus 1. Okay. So, I can say that f1 k minus f2 k into Wn k. So, if you see that x k can be represented in two parts, f1 k, f2 k, and f2 k multiply will be. So, I can say that suppose this is my f1 k, let us say this is n by 2 point dft. Okay, I will write in here. So, this is my f1 k, this is n by 2 point dft, and here is this is f1 k, this is f2 k, this is n by 2 point dft, length is n by 2. So, here I can say that f1 k and f2 k will be added together to get x of k, where k varies from 0 to n by 2 minus 1. But when it is n by 2 plus 1, I can say this is nothing but a f1 k. So, this is nothing but a minus 1, I can say, sorry, let us say give it in here, not this point. So, I can say minus 1. So, this point is x of k plus n by 2. If I say it is nothing but a f1 k minus f2 k multiply by this f2. If you see here, f2 is multiplied by Wn k every time. So, I can say f2 is multiplied by Wn to the power k. So, whatever the f2 k number is there, so n by 2 point will be there, n by 2 line will be there, and here will be n by 2 line. Now, every line will be added together in here up to n minus 2, and every line will be subtracted with this one. So, this one will be multiplied. So, if I draw the picture directly correctly, you can see this will be this kind of picture, sorry. So, this is n by 2 point dft, this is n by 2 point dft, forget about the signal. So, this I get x0, x1, x of n minus 2, x n by 2 to n minus 1. So, I can say, and this one, this f2 is, let us say this is z, is multiplied by omega n k. So, k equal to 0 to k equal to n by 2 minus 1. Clear? So, what I have to do? Instead of direct computing x k, I divided the sequence in a two part. Sequence is varies from 0 to n minus 2, because length of the even signal is n by 2, length of the odd signal is n by 2, and then I compute n by 2 point dft. Then I know the output is nothing but every n by 2. First n by 2 is f1, second n by 2 is f2. So, f1 plus f2 for k equal to up to n by 2 minus 1, and next one is f1 minus f2, and every time f2 will be multiplied by Wn to the power k. So, if I say in time dissemination in time algorithm, what is the computational complexity? So, what is the stage required for dissemination in time algorithm? So, stage 1, number 1 stage is that I have to compute n by 2 point DFT for F1k and F2k. Then second step, F2k will be multiplied by a number by a complex factor which is omega n to the power k. And third stage, I have to add them, either F1 add them F1 plus omega n k F2k. So, second stage I am producing omega n k F2k. Now, F1k once will be plus F2k for k equal to 0 to n by 2 minus 1 and F1k minus omega n k F2k for k equal to n by 2 minus n by 2 to n minus 1. So, I get from these two equations I get x of k. Now, what is the computational complexity? This stage instead of I required n by 2 into n by 2 complexity into 2 because 2 DFT, complexity of F1 is n by 2, complexity of n by 2 into n by 2, complexity of F2 is also n by 2 into n by 2. So, n by 2 into n by 2 plus n by 2 into n, so 2 into, so n 2 into n square by 4, I can say n square by 2. Okay. Now, what is the complexity in second stage? Number of multiplication. So, here number of multiplication is, I can say n by 2. So, I can say total multiplication is n square by 2 plus n by 2. So, total number of multiplication required, the methods I said is n square by 2 plus n by 2, that instead of n into n. So, I can say if the n is quite large, then I can say it is reduced by half. If the n is very large, so it is reduced the complexity by 50%, half, 1 by 2. So, if you see this is a single stage. Now, this stage can be repeat for another one. What is the meaning? Meaning is that now I can say F1k whose length of the DFT is n by 2, again can be applied the same principle, can be divided into two parts. So, n by 4 and n by 4. So, F1k has a sequence, that sequence can be treated as a signal and take it n by 4 into n by 4. Similarly, F2k also can be computed. So, each stage, so n by 2 is one stage and the n by 4 is another stage, n by 8 will be another stage. So, number of stage depends on how you express n. If n is equal to 8, then I know number of stage is 2 to the power 3, 3 stage is there. I can divide the signal in 3 stage. So, when I computing F1k, what are the signal index? Let us say F1k time domain signal is small f1n is nothing but a x0, small x0, small x2, then is nothing but a x of 2 into m, varies from 0 to n by 2 minus 1, and f2n is nothing but a x1, x of 2m plus 1. So, I accessing those index which are odd, varying from 0 to n by 2 minus 1. So, now this F1 sequence again is divided into sequence. So, this division is going on and ultimately I get the signal where it is not divisible, this 1. So, if I say n is equal to 8, then first you divide the signal n by 2, n by 2, 4. So, 8 is divided 4, 4, then 4 is divided 2, 2, then 2 is divided 1, 1, 1, 1, 1, 1. 1 odd signal, 1 even signal, 1 odd signal, 1 even signal. So, if you see that how do you do that? So, now let us say take an example 8-point DFT, then you can understand how this Radix-2 algorithm is work. Let us say I am not showing you the slide, I will show you the slide later on. Let us say I have a signal xn and I want to take 8-point DFT, n is equal to 8 and I calculated x of k. So, what is the signal are there? X of 0, index 0, x1, x2, x3, x4, x5, x6 and x7. So, number of 8 signals are there. Similarly, xk also x0, capital Xk, x1 dot 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 up to x7. Now, I said dissemination in time. So, every time I divided the signal in 2 parts. So, I want to group f1n is the even signal. So, I want to access the index n which is expressible by 2m, m varies from 0 to n by 2 minus 1. So, what is n by 2 in case of 8 by 2 minus 1 means 4 minus 1 means 3. So, if m equal to 0 I get x 0, if m equal to 1 I get x 2, if m equal to 2 I get x 4, if m equal to 3 I get x 6, done. 0. So, m varies from 0, 1, 2, 3. Now, what is odd signal f2n? It is n is equal to 2m plus 1. So, m is 0, that means x of 1, m is 1, x of 3, m is 2, x of 5, m is 3, x of 7. So, this is 4 number of signal, here also 4 number of signal. Now, again this f1 can be treated as a sequence whose index is 0, 1, 2, 3. So, is again I divided into G1 sequence which is even and f1 is divided by G1 and G2. So, G1 in even sequence again if I consider 0, 1, 2, 3. So, it will be x0 and x4. G2 will be x2 and x6. Now, again if G is divided by another stage, so there let us say V1. So, V1 n small v1 n will be x0 and V2 n will be x4. So, this is even signal, this is odd signal, further division is not possible. So, I divided the signal in this way. So, what is the group of the signal? 0, 4. Similarly, if I divided this sequence, let us say V instead of V, let us say P1, P2. So, P1 n will be this sequence. So, x2 and x6. Similarly, I divided this sequence, this is 0, 1, 2, 3. So, 1 and 5 will be clubbed together and 3 and 7 will be clubbed together. So, when I say I have an 8 n equal to 8 x0 to x7, the sequence is clubbed like this x0 with x4. then x of 1 with x of 2 with x of 6. So, this is even sequence, this is odd sequence, even sequence, odd sequence. Then x of 1 will be clubbed with 1 with 5. Then x of 3 will club with x of 7. Now, if you see at final the length of the DFT n is equal to 1, n is equal to 1. So, the signal, so length of the DFT is 1, so the signal is even sequence length is 0 and odd sequence length is also 1, signal length, single length sequence. So, when I want to compute this one, let us say this is xk, let us say. So, I want to compute xk. So, x0 is equal to, I can say even 0. So, let us say this is represented by let us say V1 and V2. So, x0 is equal to V1 0 plus V2 0 into Wn k is 0. So, what is V2 0? So, what is V1 0? x0. What is V2 0? x4. So, if I say that x0 k equal to 0, that means these two will be added together and this will be multiplied by Wn to the power 0. So, I have multiplied x4 with Wn to the power 0, then added up with x0. Now, what is this one? So, what is x1? x1 I know this sequence is periodic. So, I can say x1 is nothing but a V1 0 minus V2 0 into Wn to the power 0. So, I have to minus instead of plus. So, I have to minus 1 and then. So, this will create this point, it is nothing but a x4 multiplied by Wn to the power 0 and multiply by minus 1. So, it is create minus x4 Wn to the power 0, which is this part. Similarly, the same thing will be happen in here also, same thing in happen in here also, same thing happen in here also. Now, if I say this length, here I get length of the DFT is 2. So, here I get x0, x1, x2. If I say x0 is nothing but a this one will be multiplied by this one. So, I can say x0 will be then x of 0, or I can say this output, this output is let us say V1, so V capital Vk. So, Vk0, Vk1 and this is also let us say instead of Pk0 and P1. Now, I am saying that these two sequence again will be combined, this one will be combined with this one to get that. So, Vk and Pk will be combined in positive and then again it will be multiplied by 1, we will get this one. So, we get this one. But what is required? Again I have to multiply by Wn to the power k. Now, here if you see Wn to the power k, so k equal to what? Here k, what is the length? Length is here, length is not n, here will be n by 2. If we see, when we calculating f1 k and f2 k, we multiply by Wn to the power k. The length of the DFT, when it is f1 k length is n by 2 and f2 k length is n by 2, then it is Wnk. But when it is n by 4, then it will be Wn by 2. So, Wn by 2 to the power k. So, which is nothing but a Wn to k. So, k equal to 0, it will be Wn 0. Here it will be Wn to the power 2. K equal to 1. So, 2 will be there. So, I can say that that whole things will be look like this: W0 butterfly, W0 butterfly, W0 butterfly, W0 butterfly. Here I am combining. So, this is omega 0. So, omega n by 2 k. So, omega n by 2 0, omega n by 2 1, which is nothing but a omega n square. So, it is nothing, sorry, not omega, w n square, w square, not omega, w square. So, this w square will multiply with this line minus 1, I get this one. So, I get x 0, let us say I get another, let us say f 0, f 1, f 1 0, f 2 0, f 3 0, f 4 0, sorry, f 1 0 1, f 1 2, f 1 3. Here I get f 2 1, f 2 2, f 2 0, f 2 1, f 2 2, f 2 3. Now I combining at the 8th output stage. So, I know f 1 plus f 2 in case of x 0 up to n by 2. This portion it will be plus and this portion it will be minus. Similarly, here also this portion plus, this portion minus, here this portion plus, this portion minus. Now, what should be my algorithm? So, my algorithm, so what I observe and what should be my algorithm? So, if we see that if this is stage 1, so signal is flow from this side to this side, but when we understand from this side to this side. How we understand? We understand that n by 2, again I go for this, so again this side it will be expand, and what is the signal flow? We take the 2 point DFT, then 2 point combine, then 4 point combine, I get the complete DFT. So, signal flow is like this stage to this stage, because this portion I know, I can calculate this weight factor and I can flow the signal in this direction, I get this one. If you see, every stage there is a 4 butterfly, this is called butterfly. If you see the 2 wings of butterfly, so that is why it is called butterfly. So, this stage there is a 4 butterfly. So, if I say in general, for every stage there will be a n by 2 number of butterfly. If it is 8, then if you see it is 4 number of butterfly. If it is 16, there will be every stage there will be 8 number of butterfly. So, observation is that here also that if you see 4 butterfly, there this line along with this line 1 butterfly, this line and this line another butterfly, this line and this line 1 butterfly, and this line another butterfly. So, 4 number of butterfly. Here also if you see the 4 number of butterfly, this line with this line, this line with this line, this line with this line, and this line with this line. So, there is a 4 butterfly, and every butterfly will look like this. This is the generalization form of the butterfly. So, here is the input and here is the output. So, initially I take input x 0 and x 4, I compute w n to the power 0 which is 1. So, I can say I know the value of x 4, I know the value of x 0. So, I can say this one is nothing but a x 0 plus x 4, and this one is nothing but a x 0 minus 1 minus x 4. So, I got this point and this point. Then again this one will be, this is the output. So, this is A and this is B. Now, B will be multiplied with W n k again. So, next stage in case of 4 point, it is nothing but a W n square or 1 0 or W n to the power square. So, there is a 2 index 0 and square. So, I know the value of W n, W n is equal to the power minus j 2 pi by n is equal to 8. So, 2 pi by 4. So, in this case it will be 1, but in this case it will multiply by 2. So, it is pi by 2, which is minus j. So, then I can say that this portion will be multiplied with minus j and this portion will be A and store, and it will be propagated for the next stage. And then again this one will be multiplied with added with this one, and this one again will be multiplied with this one. I have got already multiplication I got. So, this one will be minus with this one, I get this 2. Then again this one, sorry, I guess these 2, then this one with this one and this one with this one. So, 1, 2, 3, 4 I get like that way. So, now I can say the observation that if for n equal to 2 to the power v, there are n by 2 number of butterfly for every stage. And how many stages will be there? Log 2 n. If it is 8, n equal to 8, there is a 3 stage. If equal to n equal to 1024, n equal to, then there will be a 10 stage, because 1024 is nothing but a 2 to the power 10. So, it is nothing but a 10 stage. So, each butterfly involve one's complex multiplication, where Wn will multiply with F2k. So, since the length of the butterfly is 1, so I can say 1 complex multiplication and 2 complex addition. One is addition, one is subtraction. Subtraction is also addition. So, I can say how many stages will be there? The stages will be n by 2 number of. So, I can say that log. So, how many stages are there? So, there will be a log 2 n number of stages is there. Each stage required 1 number. So, I can say it is nothing. How many stages are there? N by 2 number of stages are there. So, n by 2 into log 2 n. Each stage n by 2 butterfly. Each butterfly 1 complex multiplication. How many stage? Log 2 n. How many butterfly? N by 2. So, I can say the number of stage multiply by n by 2 is the computational multiplication required for computing discrete Fourier transform using FFT algorithm. Now, one butterfly operation is performed, then output can be stored in a input, and another one is that input signal index should be bit reversal. So, in the next lecture I will explain what is the meaning of bit reversal. Okay? Thank you.